Okay, so we have delta W sub current. That's telling us how many, how much to change um, the current value of the weight. Okay, and we did this just in a simpler example where we only had one weight. Okay, now back propagation rules. The back propagation algorithm takes the prediction error, which is the actual minus the output, for a particular record. So we do it for one record, and then um, we percolate that error back through the network, assigning partitioned responsibility for the error. So there was some error, and we want to basically spread that error throughout all the, or spread the responsibility for that error throughout all the different connections, or basically throughout all the different weights. The weights on these connections are then adjusted to decrease the error using gradient descent. In other words, why do we use gradient descent? Well, how do we know how much to change each of the weights? Well, we'd like to change the weights, so if there's a weight that's going to make a big difference when we change it, we'd like to change that more than if there's a weight that's not going to make such a big difference. And that's exactly what the gradient descent will do. If you change it a little, I'm sorry, if you get a big change, that means a big gradient, then you'll change that weight a lot. And so anyway, so it spreads out the responsibility in this way. Um, Now this part actually here, all right, using the sigmoid activation function and gradient descent, Mitchell derives the backpropagation rules as follows. All right, Mitchell, by the way, because I didn't go through this, so I don't completely understand this part. Um, so I'll give you the reference, which is right here. Tom Mitchell, Machine Learning, McGraw-Hill, New York, 1997. So I'll show you the part that I'm not quite sure about. Um, Sorry. Okay. Bring this back here. So using the sigmoid activation function gradient descent, Mitchell derives the backpropagation rules as follows. So we were talking about how to adjust the weights, and we're talking about each weight, so we list them as Wij. Um, and we take Wij, the current value, and we change it by some amount, and we get the new value. And how much is this? Where delta Wi sub j is equal to eta sigma sub j, I'm sorry, delta sub j and xij. Now remember that xij was the value at each node. We know that eta represents the learning rate, and xij signifies the ith input, to node j. Now I might be wrong about this, and if anybody has any comments about this, please leave a comment on on our website. But as far as as far as I know, xij should be equal for all j's. So xi1, xi2, xi3, xi4. Maybe that's not right. Anyway, if anybody has a comment about that, let me know. Okay, and finally, but what does delta J represent? And this is the part I don't understand for sure. And if you want to read this in that Mitchell reference, go ahead. Uh, and you can explain it to our class or put it in the comments. Uh, the component delta sub j represents the responsibility for a particular error belonging to node j. So this is exactly what we said. This tells us how much responsibility should belong to a particular node or to a particular weight. The error responsibility is computed, and this is the part I have no idea where this comes from, is computed using the partial derivative of the sigmoid function with respect to net j. Now, personally, it seems to me like it should be computed using what we were just talking about, which is the gradient descent method or the partial derivatives, but not of the sigmoid function and not with respect to net j. So I don't know about that, but maybe that is explained in that reference, and takes the following forms, depending on whether the node in question lies in the output layer or the hidden layer. So remember, the nodes could be in the output layer or in the hidden layer. So if it's in the output layer, you use this formula for delta sub j. And if it's in the hidden layer, you use this formula for delta sub j. And that's all I'm going to say about this because I don't really get it, this part. And I haven't looked at that reference. Where this refers to the weighted sum for the error responsibilities. Okay, anyway, I'm going to leave that. And if anybody can explain it in the comments, we'd like to hear it. Okay, and finally, also note that backpropagation rules illustrate why the attribute values need to be normalized between 0 and 1. Remember, the attribute values are the inputs, the variables values, and they need to be normalized to be between 0 and 1. For example, if income data with values ranging into 6 figures were not normalized, the weight adjustment here, delta wi sub j, this is the formula for it, would be dominated by this, right? Because that would be so big. And so just because income is measured and in, say, yen and can be a very large number, you'd get a very large change in wi sub j. So we don't want that. So we want to normalize income just to be between 0 and 1. Hence the error propagation in the form of delta sub j through the network would be overwhelmed, and learning, that is weight adjustment, would be stifled. Okay, let's look at an example of backpropagation.